In this lesson, we're going to have a look at classifying stationary points, and what you see in front of you is what we looked at in the lesson prior to this one, where we were reminded about what stationary points were, how to solve for our stationary points. And I did say at the start of that video that there were three different types of stationary points, if you remember. There were a stationary point could be a maximum, it could be a minimum, or it could be a point of inflection. Now, this word local right here is because a function might have a maximum at an endpoint that's not a stationary point. So a local maximum simply means that before and after that point, the function has a lower value. Minimum, before and after, the function has a higher value for local. Many functions have points of inflection that are not stationary. Stationary point of inflection is where f dash of x is equal to 0 at that point. Okay, so we're going to have a look at classifying. Here we go. I'll leave it just zoomed into this first example here. And because we've already worked on derivatives for quite a bit, I've got the calculations for the derivative already. Please feel free to pause the video and read through to make sure you're okay with it. But you can see here that through the derivative process, we determined that there's a stationary point at x equals -2 and x equal to 1. Now, the first derivative test effectively gets you to order these derivatives in order. So I'll just change colour so it stands out a bit. I'll just go to orange. So in the first row, we're going to have values of x, and I'm going to have a gap followed by -2, which is my smallest x coordinate of the stationary point, and then another gap, and then I'm going to have 1, and then I should have another gap after this, to be honest. So we put our stationary points in like so, and in between them we put whatever values we want to, as long as they are in between and as long as they're fairly simple to calculate. So I'm going to choose 0, and then that's not the other side of -2. I'm going to choose -10, then I'm going to choose 0, then I'm going to choose 1, then I'm going to choose 2, something like that. Maybe even 10. No, I'll leave it as 2. Okay, so what I do then is I put down my derivative row like so. Now, at the turning points -2 and 1, we know that the f dash is equal to 0, so I can put zeros in here. Now I'm going to substitute my numbers into f dash of x to see what these values here are. So this one, and this one. Okay, so here we go. We've got, if I put in -10 into here, I'm going to have 100. -10 is 90, -2 is equal to 88. So in a test situation, if you can easily calculate the number, calculate the number. If you can look at the number and the substitution and you can see it's positive or negative, feel free to put a plus or a minus into that spot instead. I do encourage you to actually calculate the number if you can, simply because if you make a mistake, this will figure out what that mistake is. Okay, now I'm going to substitute 0 in. So we've got 0 squared is 0, plus 0 is 0, -2 is -2. So I've got a -2 here, and then I've got a 2 for this spot here. So 2 squared is 4, 4 plus 2 is 6, 6 minus 2 is 4. So we've got the value 4 here. So we've got a positive gradient, nothing, negative gradient, nothing, and a positive gradient. So in terms of f, which is my third row, I'll be saying positive means it's going up, and then stationary point, and then I've got a negative value, so it's going down, then a stationary point, and then I've got it going up again. And I don't quite have enough room for this, but I would then be stating that there's a maximum at this value and a minimum at this value. So that is classifying the statement. So technically speaking, I should say it's a local maximum and a local minimum, but nevertheless, max and min will do for this. Hope that makes sense. That's the first derivative test, and you can always apply this first derivative test to whatever function that you're given. However, there is a more efficient test called the second derivative test. It's usually more efficient. And what I'm going to do in this video is I am going to state how one uses it, and then in a follow-up lesson, probably in class, because it's a bit tricky to work out, I'm going to tell you why it works. So first of all, what is the second derivative? The second derivative of a function is the derivative of its gradient function. So if we have a function f of x, then the gradient function is f dash of x, and then the second derivative is f dash dash of x. Okay, so the function, first derivative, second derivative. Okay, or in y notation, y goes to dy by dx, gradient function, or the first derivative, and d2y dx squared is how we notate the second derivative, or the gradient function of the gradient function, if you like. Not that I've ever called it that, and I never will again. It was horrible. Okay, let's have it all out, zoomed out, and we'll have a look at slide 4 using this test. So this is the critical thing. If f dash of a equals 0, in other words, if I have found a value for x called a, such that it is a stationary point, then if the second derivative at that point is less than 0, if this is negative, then we have a maximum at x equals a. Okay, we have a maximum. So think of it, this is how I think of it, is that if f dash dash of a, if the second derivative is less than 0, then we have a maximum because we have a frowny graph at that point. If the second derivative at the point a is greater than 0, then we have a minimum at x equals a, and think of that like a smiley graph. So therefore, the stationary point is a minimum. Is a minimum. If f dash dash of a is equal to 0, then we need to go back and apply the first derivative test because it's inconclusive. It is probably an inflection like this, but we don't know it is, and we have to use the first derivative test to confirm. Okay, so keeping all that in mind, I have 4 examples, and because we've got a different video which covers these, covers how to work out the derivatives for each of these 4 examples, I've already worked out the derivative. We're just going to see how to use the second derivative test to finish up the problem. Okay, so again, just to say it again, if you want to, pause the video so that you can see how to work out the derivatives for each of these examples. This is focusing on the second derivative test. Okay, so in example 1, f of x equals sine of x, and we're told the stationary points are x equals pi on 2 and x equals 3 pi on 2. So we're starting off with the derivative of sine of x, which is cos of x, but for the second derivative test, I need to work out what the second derivative is. So f dash dash of x is equal to, so what's the derivative of cos x? It's negative sine of x. And so I write down negative sine of x, and that is my second derivative. I now evaluate at pi on 2 and 3 pi on 2 to see what's happening at f dash dash of x. So f dash dash of pi on 2 is equal to negative sine of pi on 2, and negative sine of pi on 2 is equal to negative 1, just over here, really quickly. Pi on 2 is up here, so the sine of pi on 2 is 1, so negative sine pi on 2 is negative 1. And f dash dash of 3 pi on 2 is equal to negative sine of 3 pi on 2, which is equal to positive 1, because the sine of 3 pi on 2 is negative 1, so the negative sine of 3 pi on 2 has got to be negative 1, which is otherwise equal to 1. And so we can say at that point we have a maximum because if the second derivative is negative, and at the second point, 3 pi on 2, we have a minimum because the second derivative is positive. Done, 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 done. Okay, let's have a look at example 2. Example 2, find the stationary points and state their nature. So I've already done that. I've got the stationary points here. It says find the stationary points, so not only did I find the x values, but I found the y coordinates as well. But for the second derivative test, we just need the x coordinates. So using the other notation, I have the second derivative is d2y dx squared is equal to, and I'm just finding the derivative of that. 3x squared minus 3, the derivative of that is 6x. That's it. 6x. So now we look at the second derivative at those points. So we've got at x equal 1, we have d to y dx squared, and just doing a substitution, is equal to 6. So that's a minimum. And at x equal to negative 1, should have probably done those the other way around, d to y dx squared is equal to 6 times negative 1, which is negative 6. So that would be a maximum. And that's it, all done. So it's a lot more straightforward than the first derivative test, I have to say. You need to understand why it works, though, otherwise you do get into all sorts of bother. So keep that in mind, that why does it work is coming. Okay, example 3, f of x equals 2x minus 1 all cubed. And you can see it's a chain rule problem where if I work my way down, I find out that x is equal to a half. And we have to work out whether it's a minimum or a maximum or an inflection. Okay, so first step is work out the second derivative. So f dash dash of x is equal to, so I'm using this line here. That's the most simplified version of f of x, f dash of x, 6 times 2x minus 1 squared. So the second derivative is going to be, bring the 2 down, so that's going to be 12 outside of 2x minus 1. 2 minus 1 is 1, so that's the power. And then the derivative of the inside is 2. So I've got 24 outside of 2x minus 1 is my second derivative. Okay, that's all nice and easy. Evaluate at x equal to a half, and I get 24 outside of 2 times a half minus 1. And that would be 0, right? 2 times a half is 1 minus 1 is 0. So that's equal to 0. So this is an example of where, because the second derivative is equal to 0, I need to go back to the first derivative test, keeping in mind that it's likely that it's an inflection. So I will do my really quick test here. I'll have x, f dash, and f. I need to look at a half here. So I'll just go nice simple numbers either side of a half. And then I'll substitute them into the derivative, not the second derivative, but the first derivative. So f dash of 0, so we've got here, we've got, if I substitute 0 in, I'm going to get 0 minus 1, which is negative 1 all squared is 1, multiplied by 6 is 6. So I've got f dash is 6 here. And then we know that's 0. And then when x equals 1, f dash is equal to 2 minus 1, which is 1 all squared is 1 times 6 is 6. So I've got 6 again. So I've got that as my second row, and that means I've got positive and then a stationary point, then a positive. Therefore, it's an inflection. Okay, and finally, example 4. You might be able to guess where this is headed with this one. So we've got the derivative already worked out. This is 2x minus 1 to the power of 4, so very similar to example 3. If I work out the second derivative, I'm going to do this nice and quick now to finish off the video. The second derivative is going to be 4 times 3 is 12 outside of 2x. Sorry, my bad. I'm doing it from here. 8 times 3 is 12. Oh man, 24. Be good if I could knew my maths, wouldn't it? Squared, and then the chain rule says I need to find the derivative of the inside, which is just 2. So I've got 48 outside of 2x minus 1 all squared as my second derivative. Let's find the derivative, second derivative at a half, and I get pretty much the same thing, right? 2 times a half minus 1 inside the square, in which case that would be 0 again. So we've got a derivative of 0, which remember means inconclusive. So I draw up my table again. So we've got x, and I'm going to choose 0 again, a half, and 1, picking the numbers that are nice and easy. First derivative, and then what does that mean about the function? So when x equals 0, again, I'm taking it from this line here. So when x is equal to 0, I've got 2 times 0 is 0, minus 1 is negative 1, cubed is negative 1, times 8 is negative 8. So it gives me -8 here. The half gives me 0. And when I substitute 1 in, I've got 2 times 1 is 2, minus 1 is 1, cubed is 1, times 8 is 8. I've got an 8 here. So that's going down, and then stationary, and then up like so. So this is, in fact, a minimum. Okay, so even though the second derivative is 0, we do get a minimum. And just to confirm, if I go to Desmos and have a look at, say, for example, example 3, we have an inflection point here with the stationary point being through the blue line here. But if I look at example 4, it's a real flat minimum here, but nevertheless, it is a minimum. So even though the second derivative is equal to 0, it is still a minimum. And I think we can leave it there.